Good afternoon. It is 3 p.m. in Central European Time. It is in the morning in United States. It is in the evening in Asia. We are global today, and we are global to talk about one of the most important topics when it comes to optics. We are talking about optical ground stations, both for telecommunication as well as for quantum communication. We have to say in the last few years, we have seen a major revolution in adaptive optics in space communication, and companies like our ALPAO have seen a significant growth in this sector. Traditionally, space communication using coherent techniques, which needs large detectors to collect as many photons as possible, but the increasing demands on high bandwidth have forced the space industry to redesign free space optical links and implement coherent techniques. We're going to talk to you with two of the key experts in this segment about what we do today and what we need from you to do in the future. My name is Jose Pozo. I'm the Chief Technology Officer of Optica, the global platform for advancing optics and photonics worldwide. And together with me, I have Thierry Lanz, the President of OGS Technologies. Thierry, good afternoon.
Good afternoon.
And I have Andrew Reeves, Scientific Researcher of the German Aerospace Center, DLR. Andrew, good afternoon.
Good afternoon.
It is an honor to be here with you today. We want to hear from both of you how an OGS, an optical ground station, works, but also how optics, and especially adaptive optics, are making such an important effect on this segment. Thierry Lanz, let's start with you. Let's hear a bit more about OGS technologies, about ground stations for free space optical telecoms. The floor and the attention of everyone goes to you, Thierry.
Thank you. Can I have the first slide, Alice?
Can you see this?
Yes. So thank you, Alice. I will introduce the topic by talking about optical ground stations and the importance for free space optical telecom. I will concentrate on introducing the context of free space optical telecom and what is the general architecture of an optical ground station. And this will open the way for Andrew to present the importance of the optical instrumentation, which is connected to those ground stations. Here you have a small view of the MEO station at Côte d'Azur Observatory. It was one of the first and leading proponent of ground station for optical telecommunication already about 10 years ago. And OGS Technologies is actually an industrial spin-off of the Observatoire de la Côte d'Azur. Can we move to the next slide, please? So to introduce this context, I'd like to talk briefly about the reason of switching from radio frequencies telecommunication to optic, give you an idea of the timeline and the current status, and then basically concentrate the talk on a synoptic view of the ground station and the technical challenges to meet for those ground stations. Can we move to the next one? Okay, why are we going to free space optical telecoms? There are several reasons and several disadvantages. The basic reason is we want to increase the amount of data we transmit between space and the ground, and to go from multi-gigabit per second up to terabit per second capabilities. And for this, we have to move to higher frequencies, and that's why we move to the optical. The optical offers also a much greater security. That is, the emission cone of the beam is much narrower, so it's much harder to intercept. So it provides more security to your transmission. And also, since the cone is much narrower, we avoid the basic overlap that we have in radio frequencies, which led to have frequency band attribution for satellites, and which limits the number of satellites which can emit in those frequency bands. The advantage of the laser cone is much narrower, and we don't have those limitations. And finally, it's to move also to quantum-based telecoms, where we have to analyze single photons and to provide very secure communication. And finally, both the optical communication terminals, both for onboard terminals and ground stations, are much more compact and require much lower energy, which is very important when we think about doing communication to deep space, Moon, Mars, or deep space probes, where the amount of energy you need to communicate with them is very important. Of course, there are disadvantages and drawbacks, especially atmospheric losses. Clouds are not transparent to lasers, contrary to radio frequencies. And there's the issue of atmospheric turbulence, which disturbs the wavefront and led to losses. And those losses will be addressed with the adaptive optics system that Andrew will talk about later. And finally, the requirement for pointing and tracking are much more demanding. And basically, the reliable and precision pointing is everything for optical telecom. We can go to the next. So a brief timeline of where we are in optical telecom. I would say it's very, it's just a small example. It doesn't intend to be exhaustive, but to give you a general timeline of the development. In the year 2000-2010s, basically, we had a number of proof of concept in basic research. 2014, the Lunar Laser Communication Demonstrator by NASA. SOTA terminal aboard of microsatellites from the NICT, which created the first optical link between microsatellites and a ground station in Europe, which was the ground station at Côte d'Azur Observatory that I showed. And in 2017, the MISIUS satellites, the first quantum key distribution from space. So those proofs of concept led to now in the 2020s to industrial demonstrators. And some key points are the definition of a standard for optical communication terminal by the Space Development Agency in the US in 2020. Example of now the top down-to-Earth transmission with the T-Bird satellite constructed by MIT, which reached 100 gigabit per second. And next year, we will have a teleo demonstration in Europe, which aim at achieving a 10 gigabit per second bidirectional link to the geostationary orbit. Those demonstrators prepare an industrial deployment in a different topic, down-to-Earth transmission from Earth observing system, geofeeders, quantum K distribution of quantum internet network, and lunar optical comms. And we expect those deployment in the 2020s to 2040s. I put 20 to X because it depends on the complexity of the system, but we can expect industrial deployment starting in 2025, 2030. And finally, in the NASA roadmap, NASA intends to have switched completely to optical telecom by 2040. And we have the next one. So what is the general architecture of an OGS? Next one, here is the first simple case of down-to-Earth mission from the LEO orbit. Next one, Alice. So basically, what's in the past, a ground station or for optical telecom was always thought in very simple terms, that it was a telescope, and basically you buy a telescope off the shelf and you have your system. Actually, it's a little bit more complex. Basically, first thing to point out in the architecture, an OGS is a bidirectional system. You have in the down to Earth, you have the telescope to receive the signals from the satellite. So you have the telescope on the left side, which is on the mount, on a telescope mount. But you have also a beacon to basically point to the satellite, so that the satellites can point to your station. For down-to-earth system, basically the beacon can be a very low power, typically a few tens of megawatts. Basically it allows the satellites to point to the station and the station to acquire the satellite signal. Beyond that, you have an instrumentation which is in this yellow box, basically with a tip tilt mirror to correct from low frequency noise, vibration, wind, and so on. And the signal is collected on a detector, here in the simple case without any adaptive optics, and a front-end processor, which is basically a modem to translate your data. And you have a whole computer system to pilot your station. Now, the whole station is not only that. You have all the infrastructure which comes around, the protection, the dome, but also all the security measures, weather system to give you information on the weather situation, and all the security. So that's a reasonable, simple system. Now, can we move to the next one? We have special cases where you have very low flux cases, typically in the single photon mode. And this concerns basically two applications of the down-to-earth scenario. In the case of quantum telecoms, you need single photon detectors, and you can't have signal amplification because all the information is in the quantum state of your photon. You need to add also time stamping of the single photon detection to be able to synchronize your photons received at different stations. You need also not to change the quantum state of your photons. So you have to make sure that the optical ground system, the optics of your system, doesn't introduce any polarization. And finally, the big difference here is the flux is so low that you need really to put on your satellite an onboard beacon to provide a separate source for pointing and tracking the satellite, to have enough flux also for wavefront correction with adaptive optics, and finally to transmit the timing data for synchronization. The other case of very low flux is, but otherwise for quantum telecom, you can have a ground station which is reasonably similar than for classical telecommunication. In deep space telecoms, your satellite, your probe, or if you're on the moon, is very much further away. So you have to have a detailed link budget to make sure you get enough photons still for tracking and for analysis by the wavefront sensor. And this might require to have a larger telescope. We can move to the next one. The second kind of mission for an OGS can be the case of geofeeder mission, where you want to have bidirectional telecom, both on the receive end from the satellite, but also to the, an uplink to transmit. Can we have the next? Okay. So here you have an architecture which is bistatic, and the reason we have a bistatic architecture is that because the receive power and the transmit power are very much different. The receive power is typically a few 10 of nanowatts, while the transmit power is typically a few watts to a few tens of watts, in the future probably several hundred watts. So you really need to separate and to have a full isolation between the two channels, because you can imagine if you have even a very small fraction of scattered light from the transmit channel into the receive channel, you will lose completely the signal you receive from the satellite. So we designed a system which is completely bistatic with two separate tubes, and with the possibility also to have a Coude optical train to put all the transmit elements in a focal laboratory, which offer also the advantage to be in an environmentally controlled atmosphere. And if you want, this system is in the focal lab, which is at a distance from the telescope. In this mission, we need to correct for all the atmospheric turbulence. So we have two adaptive optics systems, one on the receive end to be able to inject the signal into a single mode fiber signal, which can be amplified by a standard optic fiber amplifier. And on the transmit side, you can also amplify your signal to be emitted by the TX tube. And this architecture is then also you have also a whole infrastructure around that. Compared to the previous, the simple down-to-earth architecture, here you manipulate laser with substantial power. So you really need to design all your safety equipment, all your security to deal with this amount of power to make sure you operate in the safest way. Can we move to the next one? So OJS Tech, and I will go very quickly, is currently developing a versatile optical ground station for the French Space Agency. We built it with some industrial partner. And this is tailored to the first application with satellites in 2024, with a 10 gigabit per second feeder link to a geosatellite and a 10 gigabit per second down-to-earth mission on a LEO satellite. Maybe we can, since the time is passing, go into the next slide. The current technical challenge for those optical ground stations to achieve the level of performances which are required for the optical telecom are of four kinds. First, pointing and tracking at microrad accuracy level over a long period of time is really everything for optical comm. If you don't achieve this tracking at this kind of accuracy, you won't achieve a sustained optical link. And this includes non-interoperational conditions, for example, where you have severe atmospheric turbulence or some wind. Second point, the uplink transfer at several gigabit per second using precompensation adaptive optics is yet to be shown as this kind of performance. And the Teleo experiment, which is planned for 2024 will achieve that. Third point, which is maybe not directly obvious, all those or most of the telescopes which you can buy off the shelf now are designed to work for astronomical purpose at night. If you want to do optical telecom, you should be able to operate in daytime, where the turbulence is much more severe, and you need to be able to operate close to the sun, where the background can be very important. And finally, something which is not maybe a direct technical challenge, but developing a robotic optical ground station for robust, safe, and optimized operation require a lot of developments. Can we go to the next one? I just wanted to make a quick point about the telescope size in an OGS. Often an OGS is just characterized with, well, it has a 50 centimeter telescope, so a 1 meter telescope, or 70 centimeter telescope. As I showed, there's much more around that. And we should be aware that just increasing the size of the telescope or its main mirror is not just bigger is better. There are some advantages and there are some drawbacks. Of course, if you have a larger telescope, you can operate with lower link budgets. So it's very important, for example, for lunar communication. And also you have a better contrast with sky brightness. So this is probably a gain for operating in daytime. On the other hand, if you have a larger telescope, you need you have a more demanding tracking requirement. You need a more complex adaptive optics system with more with a more complex deformable mirror. It also implies much larger mass, volume, and complexity, and a telescope of 1 meter requires much more work to develop than a 50 centimeter. The advantage of a larger mass is it's dampened vibration and it's operates with less problem when there is some wind. And finally, a larger telescope implies higher cost and longer time to deploy. If you have only one station, it's not a key point, but if you have to deploy tens or hundreds of stations eventually, the cost of each station becomes a central point. Next slide. And I'd like to leave you with some final thoughts about the OGS. It's very important to optimize the OGS design for the mission, including interoperability with different missions if necessary. It's not just you pick a telescope and it's fine. It needs to be optimized for the mission. It's essential also to have a full system design, both the space and ground segments. Often the space segment is developed first and the ground segment comes later. But it's important to design the full system together to ensure to optimize the performance. Finally, you have to plan sufficient time to deploy and test the ground segment, not only the space segment. Actually, as I was showing in the timeline, we are at the stage of industrial demonstrator, and typically to develop and to optimize the ground station takes 12 to 24 months. It's not something you can do as an afterthought when you launch your satellite, which leads to the future industrial challenge when we move to industrial deployment. We can expect that it will be necessary to be in a position to deploy tens of OGS per year. So it needs to, we need to develop all the production tools to be able to deploy complex ground station at a high rate.
Thierry, thank you very much for a very clear presentation. I have to say that we are overwhelmed by the turnout that we got today.
Say thank you.
Thank you so much, Thierry. Thank you very much, everyone, for joining. We have the first presentation. We have a second presentation with Andrew Reeves from DLR. Andrew, good afternoon also to you. But we want to take a short Q&A section here because there are a lot of questions coming to you and people deserve the answers. 126 participants right now from many different companies in the chat. Let's go for the first one. David Kaplan. David Kaplan is wondering, can you expand on the reasons for going to a bistatic optical design for a geofeeder OES? Why biostatic?
Well, it's bistatic because the main reason to do that is to have a complete isolation between the receive channel and the transmit channel. In the receive channel, the power you receive from the satellite is typically nanowatts, while the transmit channel is typically a few watts to hundreds of watts. So it's necessary, since your optical system is never absolutely perfect. Even if you have a very small fraction of scattered light in your transmit light, then you will overwhelm completely the signal you receive from the satellite. That's why we decided to have a system which completely isolates the two channels.
The second question is a beautiful one. And Andrew, I think you're going to have to add to the answer from Thierry. The question comes from Richard. He didn't put the surname or company that he works for, but I know who he is. And he's saying, is there any use made of guide stars with adaptive optics to compensate atmospheric distortion?
So the answer is probably in the future. There's currently a few activities going on to prove it. Because they've not really been used in the daytime so much with communication systems. So there's maybe some developments needed, probably higher power laser guide stars. We're involved in an experiment currently with ESA to build a demonstrator their OGS on Tenerife. Mm-hmm. And so hopefully next year or the end of this year, this should be coming online and we can start to prove it. Certainly for geolinks, it's likely they'll be useful and probably essential for LEO links because the uplink, you wouldn't have a reference for the uplink otherwise. I'll talk about it a little bit towards the end of my presentation as well.
You mentioned Tenerife. I have to say hello to my Optica corporate members, Archimea from Tenerife, also in the room. We have another question, more like a debate going on in the chat. What is the wavelength used in optical ground stations, Thierry? Is that already standardized, or are people using different wavelengths?
No, it's almost completely standardized now, around 1550. So it's the same wavelengths that is used in fiber link telecommunications. So we can use all the heritage electronics working at this wavelengths, and it has the additional advantage that basically we are in the laser safe wavelengths for the eye.
And now we continue with the program. And before everybody keeps wondering, yes, you will receive the slides. I'm getting a lot of messages like that. Yes, you will receive the slides. Thank you very much, Thierry. We stay for the final Q&A. Andrew Reeves, all the way from Germany, all the way from DLR, the floor and the attention of everyone goes to you. Tell us about adaptive optics in optical ground stations.
Thank you very much, Jose. Do you see my slide?
Crystal clear.
Perfect. Okay, great. Well, thanks everyone for coming to see me. My name is Andrew Reeves. I lead a research group here at DLR in the Institute of Communication and Navigation, which is called Mitigation of Atmospheric Impairments. We are dealing with, as the name suggests, trying to mitigate atmospheric impairments in communication links. So trying to overcome the adverse effects of the atmosphere, trying to better couple light into a fiber, into a communication system, trying to better couple light from that OGS into the satellite to, again, improve the link stability. Okay, so today I will very, very briefly talk about why free space optical communications, but Thierry covered this really nicely. I give an overview of what's going on inside the optical ground station. Again, talk about briefly the communication systems, and then this leads to the requirements of why we need good fiber coupling and adaptive optics. This image, incidentally, is on the top of our institute. It's the new optical ground station with an 80 centimeter aperture that was installed on the roof of our institute just 2021. And then we've been using it to perform some links. I'm afraid there's going to be a few pictures of it scattered through because we're quite proud of it. So again, Thierry's already touched on this. Optical communication links are really exciting because of the potential high bandwidth of the links. We don't need spectrum licensing anymore because of narrow convergence and narrow divergence. And this also makes the beam inherently more secure. And also on top of that, we can perhaps put some quantum encryption that's not just likely to be secure, but is theoretically secure. The drawbacks, of course, are that we're not so robust to weather. And of course, that atmospheric turbulence can cause some link instability. So in our institute, the various applications we're really interested in, again, geofeeder links, where we're providing some really high bandwidth link to a geostationary satellite that can distribute the internet to multiple users via RF links so that their internet doesn't stop when a cloud goes by. The geofeeder link concept does require that we have multiple ground stations. One ground station link can probably support the bandwidth required for all the users in a kind of foreseeable system. However, we'd still need multiple ground stations, and there's this interesting study done a few years back about how many ground stations we'd need to support a geofeeder link, such that if you correlated all the cloud coverage around Europe, how many ground stations would you need and where would they have to be, such that you'd always have at least one link available with kind of 99.9% uptime. And you see you've got, you need about 11 ground stations, and any one of those can support the full bandwidth required for the constellation. However, if you were to use RF links for that same feeder link, you'd need an increasing number of links. And that obviously comes with drawbacks in terms of spectrum, etc. We're also really excited about quantum encrypted communications, mainly focusing on really efficient downlink into the ground station and to a single mode fiber. And also you can imagine a lot of applications with high bandwidth downlink from LEO satellites. Perhaps they're doing Earth imaging and they want super high resolution images of the world. Okay, so let's dive into the OGS. Again, that's a diagram inside our OGS. We have a nice CUDE lab, and we'll go into that in a little bit. So the very, very high level overview, the OGS is going to receive light from a satellite. That's going to go into a communication system. It's also going to transmit light from a high power laser, which is going to be in some way modulated so that it's transmitting data. And that's going to go up to the satellite, and we're going to connect the whole thing to the terrestrial network so that we're actually giving the satellite the internet. That's typically the application. And currently, with ground stations doing tests right now, these are often doing it with free space detectors. And there, the receiver ground station is relatively simple. On board, we have some fast tracking loop so that we've collected the light from the satellite. We've focused it onto some kind of photodiode receiver front end. We also focus it onto a 4-quadrant detector that can track the beam position. And we feed back from the 4-quadrant detector onto our tracking loop so that we keep the beam more or less stable. It doesn't have to be too stable because this receiver front end can have quite a big photodiode diameter. And we can use this to do amplitude modulation. So we're looking at ones and zeros from the satellite. And in the other direction, we are modulating some laser, amplifying it up to high power so it can reach the satellite and launching it from a collimator. Typically, this is glued to the side of the telescope. It launches really high divergence from a relatively small aperture. And in that way, we're almost guaranteed to hit the satellite. Even if the telescope shakes a bit or the atmosphere breaks up the light, we're almost certainly going to be sending some of it at the satellite. And then that's how we keep a stable link. To do that, we have to launch pretty high powers. So you're talking tens of watts, 50, 100 watts. And the link efficiency is pretty poor, but you have a stable link. And so in the next generation that we're looking towards, we would be trying to launch a narrow divergence and also doing coherent communications. So if now we kind of follow the path through, we're receiving light from the satellite. We're still doing fast tracking, so keeping the beam stable. This time we also include a deformable mirror, because we're going to also correct some wavefront aberrations, because now fiber coupling is important. We might also launch our TX laser from the same aperture. So maybe a little bit in contrast to Thierry's plan, we're looking more at the monostatic launch here. And then the downlink light is going to some more systems. It's a little bit more complexity here. We have a wavefront sensor, which is going to do the job of the 4QD before in tracking the beam, so feeding back to the fast tracking system, but also provide high order information about the wavefront that we can correct with the deformable mirror. We probably have some telemetry systems, so we can understand how well our adaptive optics system is working in real time. And then finally, we have the fiber coupling, which is, of course, the star of the show. And that we hope to couple as much light from the fiber, from the satellite, into the fiber and into the communication system. In the other direction, we are once again modulating a laser, this time maybe not just in amplitude, but also in phase. We have a high power laser amplifier again, and uplink beam steering, because now we have a much narrower divergence. We're going to launch from a bigger aperture, usually a sub aperture on the side of the main receiver aperture. And because we have a narrower divergence, it becomes important to actually make sure we're pointing really accurately at the satellite. We can launch, in this relatively simple case, we launch also off the deformable mirror. So we're adding a phase error to the beam before we launch it. And we also add an offset. But both of those will be corrected by the atmosphere as they go up. So by the time it gets to the top of the atmosphere, the light should have a relatively flat wavefront, should be pointing in the right direction. It can propagate up to the satellite and hopefully keep a stable link. So Thierry was mentioning about how you separate the uplink and downlink beams here. I can say just a little bit that we're currently doing links with AlphaSat, which operates very strictly at 1064, both uplink and downlink. And he's absolutely right. This is really hard. The polarization is the only way to do separation, and we've struggled a little bit. We've managed it, but you have to be really careful with all the optics. The future systems, 1550 based, we say they're 1550, but really they're in a range in the C-band. And so the separation can also be with wavelength as well. And there I see it should be a little bit more possible. It's likely we might, for instance, launch 1560 and receive 1540, and therefore the isolation should be a little bit easier. But in any case, in this new OGS concept, we have a much narrower beam so that we have a more stable and efficient link. We don't have to launch so much power per data that we want to transfer. And in the downlink, we're coupling into a fiber, which suddenly gives us a lot of flexibility in terms of how we use the light for communications. So let's look a little bit at what the communication systems are. Okay, so the obvious one is direct detection. We're seeing ones and zeros coming from the satellite. If it wants to send us a 1, it has a bright laser. If it wants to send a 0, it dims it a bit. And so in time, we see an amplitude modulated signal. Coherent detection is a little bit more complicated. We're shifting the phase of the transmitted beam. When we receive it, it gets mixed with a laser that we have at the ground station. We call it a local oscillator, which should have the same frequency. And if they're in phase, then we get a 1. And if they're not, we get a 0. And this is a very simplistic view because, in fact, the intensity or the amplitude on the phase is modulated so that you can actually have multiple points that you can use to transfer data. So this is something that's kind of normal in terrestrial fiber networks, but it's very new in free space communications. So down the bottom right, you kind of see some data. Now, I'll be honest, this isn't my speciality, but you go through various stages with the received light to separate out these different channels, more or less, until down the bottom you have 4 points. This is called a constellation diagram, which shows the complex plane of the received signal. And once you can modulate the light efficiently in phase and amplitude, then you can create as many points on this constellation diagram as you want, really. And it means you can increase the bandwidth of the data you're transferring. So this is QPSK, where we have 4 points, but then 16 QAM has 16, and this can go up and up. But you require better sensitivity for more channels. And all of this requires coupling into a single mode fiber, because then you're just using, well, you're using lots of photonic devices to do these things. So the communication system kind of chain might look a little bit like this, where this is post-coupling light into a fiber. We've coupled it into a fiber. Maybe again, we take a little bit out, so we always have real-time feedback about how much we're coupling, because adaptive optic systems are complicated and maybe it's gone wrong. You want to know it's gone wrong, or you want to have some kind of maybe online optimization. But most of the light is going towards the communication path. Some of it goes to preamplifier. So you're receiving nanowatts, perhaps. You maybe want to boost that up. And then demultiplex the light. So we don't just have to send a single wavelength channel. There's this scheme called dense wavelength division multiplexing, where we can send many different wavelengths in the same beam, and they're separated by perhaps a nanometer or so. And so you can fit a lot of wavelength channels onto the same beam, which has a very similar wavelength, so all in the C-band, for instance, but you can fit a lot of channels onto that. And so then you can demultiplex this very efficiently and then demodulate. So we're taking the data, or the light which has some data modulated onto it, and whatever scheme has been used, we can demodulate it to get some data back. We might also be using an interleaver, which I'll come on to explain a little bit. So we might have to de-interleave the data. And finally, there's some coding that's placed on top, which is really turning, I guess, Ethernet data into something efficient to send through an optical link. And we're doing the opposite in the other direction. So we're applying some coding to whatever data we want to send. It might be interleaved. Then we use that data to modulate a laser, perhaps modulate multiple channels which are multiplexed together. And then we amplify that up and we launch it from the telescope. So just a note on interleaving. Interleaving is a method we can use to try and make the link more robust to fades. So even with the best adaptive optic system, there's a chance we might lose the light for a millisecond, 5 milliseconds, 10 milliseconds. And it's not acceptable that we just lose the internet for that time or lose the communication link. So with interleaving, we can try and spread out the fade so it doesn't just affect whole packets. So if we take our data that's come in from the coding and we arrange it, you can imagine it being arranged in 2 dimensions in some memory of a small FPGA or computer, and you have multiple packets. If you lost a whole packet of data, it's catastrophic because the coding happens inside a packet, and the coding can recover if a tiny bit of data is lost in a packet. But if you lose a whole packet, this is really bad. So we take the data and we rearrange it, and we interleave it so that the rows effectively become columns, if you're thinking about it in 2 dimensions. And now we could think of interleaved packets, which contain a little bit of data from all the original packets. And then when we send it, we send a stream of all this data mixed up. And if we have a fade and we lose some data, well, this is bad, but we don't lose a whole packet. We lose a little bit from a couple of packets, and the coding is designed such that it can cope with that. And fitting an interleaver into the communication system is very dependent on how we expect the optical channel to look like. So if we could guarantee a completely stable channel, perhaps we don't need an interleaver. If we think we can keep fades to under a millisecond, then you might design this such that the length was about a millisecond's worth of data. However, as the data rates increase, so 10G, 100G, whatever, then 1 millisecond's worth of data gets bigger and bigger. And then this becomes a really interesting challenge, actually, to get adequate memory rates so that the interleavers keep up and that you can write and read the data as quickly as you need to. Okay, so I've talked mainly about coherent communications, which is a form of classical communications. But of course, another big driver is quantum communications. Now, I'm certainly not an expert here, but as a very brief overview, the idea is that quantum computers might at some point soon break all of our classical encryption techniques. But quantum key distribution can be used in a way to provide a key which is theoretically unbreakable, and will never be able to be broken even in the future. And so there's a really well-known protocol called BB84, where we choose some different states. Usually these are polarization states, and we send some random version of the states from Alice to Bob, and Bob detects them in a random way as well. And by comparing their results, they can exchange a key. And the idea is that then once they've got a key, they can communicate more quickly over a classical channel, but they use the key that they've transferred in the quantum link to be able to encrypt data. And this requires some new instrumentation at the OGS. So for instance, something that's becoming quite popular, these superconducting nanowire single photon detectors, which are super exciting because they can detect a single photon, are very efficient and have really high time resolution, but they're a little bit difficult to deal with. You have to get them really, really cold. And also you have to pay attention because they're so sensitive that any background light could just blow them up. So you need some really good filters there to make sure you're just seeing the photons that you want to. Okay, so on to a little bit about adaptive optics. Adaptive optics is a way that we correct for aberrations in light caused by atmospheric turbulence typically. So when the light comes in the telescope, turbulence in the atmosphere, which is caused by temperature fluctuations in the air, has imparted some phase disturbance on the light we receive. So if we tried to focus this light, we'd end up with a big blurry spot, which is terrible to couple into a fiber. However, when we receive the light, we bounce it off a deformable mirror, which we arrange such that it will take the shape to correct the light. And then we should have a more or less corrected wavefront. It won't be perfect because our control loop's not perfect, but it should allow pretty efficient coupling into a single mode fiber. Of course, we have to pick a little bit of light off onto a wavefront sensor, which is going to detect the residual errors so that we can then, on the next iteration, update the deformable mirror. And we need some control computer that will process the wavefront sensor measurements to produce the next set of actuator commands for the mirror. So down here, you see a nice ALPAO DM192, which has 192 actuators, which we're using in our lab upstairs, and a Schacht-Hartmann wavefront sensor set up using a Xenix Cheetah camera because it can run very quickly. Typically, this is running in a closed loop at multiple kilohertz. Adaptive optics is a technology that was really matured in astronomical applications. And so it's interesting to think about how it's different from the systems that are used in astronomical applications. So in astronomy, for instance, telescopes are typically situated in locations where it's really cherry-picked to be the best locations in the world because there's very little atmospheric disturbance in general. So that's often very high altitude where you're above a lot of the stronger ground layer turbulence. However, in communications, we're almost choosing the worst sites. We want the places that are next to terrestrial, high bandwidth terrestrial communications, probably cities, which are not known for their good turbulence properties. And this means that the turbulence strength will be significantly greater for communication scenarios. So we use this value R0, called the Fried parameter, to measure how strong the turbulence is. In astronomy, you're somehow dealing with 15 to 30 centimeters. R0 changes depending on what wavelength you're looking at. So you have to think about which wavelength, but that's at the wavelength the astronomers would be using. For us, it's maybe 5 or 10 centimeters. So a lot stronger. Perhaps even worse, actually, down depending on what elevation angle we're looking at. We're also potentially looking at low elevation targets, like a LEO satellite that's just come over the horizon. And then we look through a greater bulk of turbulence. So it just naturally gets stronger as well. And this also means that the turbulence coherence time, so how long it takes for it to change a significant amount, is a lot shorter in communications. And so the turbulence is changing more quickly practically. And this requires us to have a much faster iteration rate. On the other hand, there are some things that make adaptive optics and communications a little bit easier. We're typically dealing with smaller telescopes, so somewhere under a meter perhaps, whereas astronomers are now in tens of meters. And this means we don't need quite as many actuators and wavefront sensor measurements, although saying this, this might increase actually. This is maybe a little bit optimistic, and these numbers will keep going up as we want better and better performance for coupling into a fiber. One thing that should stay the same is that we almost always have a nice bright reference source. Astronomers spend a lot of time wondering how they can optimize their wavefront sensing algorithms and their wavefront sensing detectors for really, really faint sources so they can look at the faintest things in the sky. We should always have quite a nice bright laser pointing at us from the satellite. Wavefront sensing is really critical in the adaptive optics system. We're using it to measure the phase distortions so that we can correct them. The typical method is to use a Schack-Hartmann wavefront sensor, where we take the aperture of the telescope, focus it onto a detector with lots of lenslets, and then we track the focal spot of each of the lenslets. And as they move, this tells us about the gradient of the wavefront across that particular part of the telescope. And this is quite a mature technology. However, when you're dealing in stronger turbulence, again, this can maybe go a little bit wrong. So as you see on this is some data from a horizontal link that we were operating a few years ago through turbulence of maybe R0 of about 3 centimeters. And you see there's scintillation. So some of the subapertures are really bright and some are really faint. And this makes it really hard to efficiently do centroiding to track those spots. And then what you can't see as well, but what might be happening is this idea of branch cuts in the phase where you have almost lines of an infinite gradient. So you just have discontinuities in the phase that are postulated to happen in strong turbulence, but it's very hard to detect. And in any case, a Schack-Hartmann detector couldn't deal with them. So one bit of research we're looking at is better wavefront sensing devices. One way to do it would be to look in the focal plane. And a few years ago, we published a paper on this where we were looking at the focal plane and using this as a prior to very quickly iterate a fast deformable mirror and then use ultimately the light into the single mode fiber as a metric for the system's performance. And so this is going towards what's sometimes called wavefront sensorless adaptive optics, where you're just iterating on a deformable mirror to try and improve the coupling without explicitly measuring the phase. Or another method is to actually directly measure the phase rather than measuring the phase gradient. You directly measure the phase, and you can use an interferometer for that. But of course, you need a reference for the interferometer. You can make a self-referencing interferometer like a Mach sender. This is something also that's in a laboratory stage of testing, and it's likely will start to be tested more in the future. Here, anything like a branch cut wouldn't be a problem because you just see the phase directly. However, there are other issues, like you need to focus some light through a very small pinhole to create a reference. But if the turbulence is very bad, you'll get very little light through the pinhole. So your reference will almost disappear. So there's still some research to be done here, but this is a really hot topic in adaptive optics for free space optical communication, because it's thought that, especially again, low elevation LEO links, it just won't happen with the Schack-Hartmann anyway. Okay, a final point to mention in optical communication adaptive optics is the point ahead angle. So we kind of touched on this before in a diagram you saw, where we're launching our laser in a different direction from where we're receiving it because the satellite's moving. Even in a geostationary, where it looks like it's staying in the same place, we still have to point ahead of it a little bit. And this means that if we use the downlink beam as a wavefront reference, and we only observe it there, and use the scheme I showed before, where we just project off the same deformable mirror, then there'll be some error in our correction because actually the turbulence that both are going through is quite different. And the two are separated by what's typically called a point ahead angle. And this changes depending on the link type. So for geostationary links, it's about 18 microradians. For LEO links, it can be up to 50. And a potential solution is to use a laser guide star. So here we launch a laser in the direction we want, which is the transmit direction. And we observe the backscattered light, or for a sodium laser, we observe the light from the mesospheric sodium layer. And we use that as our wavefront reference. However, some of the ramifications of this maybe haven't been completely thought through yet, because that whole scheme we showed before will have to change, and we'll have to have almost two separate independent adaptive optic systems running, one for the downlink, one for the uplink, to pre-distort the beam as it gets to the satellite. And then finally, just to show you the innards of an OGS, this is inside the QD lab of our Optical Ground Station, which was mainly installed last year. We have a fairly complicated lab setup where we receive light from our telescope. So there's a QD path just more or less where my mouse is that then projects it onto the bench. We do fast tracking from a steering mirror here. Do you see my mouse? Sorry. Yeah. We have the option to pick off some light into a whole path here where we can do telemetry. We have a really high order wavefront sensor that's in open loop, a pupil imager, photodetectors to measure absolute power. We're also correcting the downlink here in the deformable mirror. And then we go to a fiber coupling area and wavefront sensing, where we have wavefront sensor camera, focus camera, so we can see how the adaptive optics has done, and the fiber coupling, of course. And we also have a setup here that we're just installing and commissioning now, where we're going to launch the same laser from the same path and hopefully test a pre-distortion concept. But you see here, this is some light from AlphaSat on our focus camera without our adaptive optics system on. And then when we start the correction, you see we're coupling, or we managed to condense the light into a much smaller point. This inner circle represents more or less the position of the single mode fiber in the focal plane. And you see we've massively decreased the size of that blob, and clearly we'll be coupling a lot more light into that fiber. Okay, so to very briefly summarize, an optical ground station features a lot of complex systems so that we can efficiently couple light into the communication system and potentially improve the stability of the uplink as well. As we move forward, it's likely that communication systems will be coherent, and we'll want to do more quantum key distribution, and all of this requires really good fiber coupling, which requires adaptive optics. And there's a lot of research to do in adaptive optics to make it even more stable and improve the link.
Thank you very much, Andrew, for a great presentation. Thank you so much. And thank you, Thierry, for the presentation. We always like to start on time and to finish on time. We are very strict on that. However, I have so many questions in the chat, and I owe them to give you answers. So I'm going to go quickly through the questions. Thierry, you're with us. Please also unmute yourself and open the camera. Fantastic, you're here. Please give us quick and short answers, because we have a lot. First question, I think it's for Thierry, from Carlos Lopez. Could it be possible to upgrade current GEO and LEO satellites for optical communication, or is new development needed?
No, you need an optical terminal, and you can't it's not software upgrade. You need new hardware, so it can be put on new satellites that you launch. Those terminals exist, but you can't upgrade current systems.
And what further limitations for placing OGS in urban areas are there? This is from Alina Rishu.
Well, the biggest issue is the turbulence will be much more severe, which would require a much more robust adaptive optics system. And the typical R0 that was given by Andrew in a city can go down to something like 2 centimeters. So it's really require a robust AO system.
I move fast. Richard Soden from Keysight is wondering, is there any Doppler compensation applied? And if so, how? For communication to LEO satellites? Doppler compensation.
Not right now. I don't know if it will be required. It will be effectively a piston term on the light, I guess, which shouldn't affect. I don't think it will be fast enough to affect the communication system, and it wouldn't affect the general light efficiency of the link. So I don't think so right now.
Is there any work on stray light mitigation. That's from Patrick Thompson.
So yes, that's what we do
Stray
a
light
lot of,
mitigation.
making that system work. Do you mean stray light for the?
For the monostatic
no,
systems.
But yes, there's a lot of work. We're looking at it both from the sense of making sure the uplink beam doesn't interfere with the downlink beam, and also making sure the quantum detectors see only the light from the satellite, and they don't have sky background interfering in the measurements.
David Kaplan, can you comment on the optical filtering used and polarization state accepted on the downlink receiver and tracking pads? Optical
It really
filtering
depends
used.
on the system. For AlphaSat, it has a very specific polarization system where you have to launch one polarization state and it launches the other. And so you can use those polarization states for beam separation. But yeah, it depends on the satellite and the scheme used.
Let's talk about deformable mirrors. Two key questions here. Scott Merritt and Yaya Sagar. How does a deformable mirror handle the power of an uplink? And how fast can you modulate a deformable mirror?
So for the power in the uplink, right now we're launching on the order of tens of watts. And then the DMs are, so we use ALPAO DMs right now, and they're typically a number of centimeters big. So actually the beam density, the power density isn't huge. So it's not so bad. In the future, if you wanted to launch lots of channels, it's an issue, and it's something I think ALPAO are looking at, but I don't know.
Yaya Sagar, is the uplink beacon single mode? As it passes from the atmosphere, can it change its mode? And does that matter? Is the beacon single mode? Do we use multimode in any way in these communication links?
Not typically.
No, we don't.
Some people are looking at it, but
how is the synchronization or timing management achieved between the adaptive optic corrections and the signal modulation detection?
So the adaptive optic system runs at a much lower rate than the signal modulation, so you don't have to worry about it. Run the AO system as fast as you can. It'll never be as fast as the communication modulation.
A link question to that comes from Patrick McCarthy. What kind of processing delay do you see?
In the AO system, it's
yes,
at least one frame. You need to let the wavefront sensor integrate, so you already have at least a frame. Typically, we assume two, but we have our real-time control system down to about 50 microseconds.
Okay, this question I think is for both of you, but because I don't know the answer. What is the R naught, the R0, the R naught in the atmosphere expected in a city in daytime?
As Thierry said, it's around 2 centimeters. It really depends where, but yeah, 2 centimeters wouldn't be unexpected, maybe even lower for worst case.
Yes.
Okay, let me. I'm gonna apologize for all the people who are submitting questions. We are gonna give you all the answers written. I'm gonna finish with one final question for all of you, which is, can you tell us from Kristen Link some of the challenges if any, encounter with adaptive optics today? Andrew, any challenges, any problems that you have, anything that you need from companies like ALPAO?
So from ALPAO, we need faster DMs and that can cope with high power. And also the main challenge is the wavefront sensing, I think, is finding how to make the wavefront sensor work when the turbulence is really strong.
Thierry, Andrew, thank you very much for a great session. I would like to ask everyone that is in the chat, I put my email in the chat. If you could send me an email with one line of what you thought about this meeting and how could make it better, that means the world to us. Thank you for the support that you're giving to Optica, building this global industry association. Let me remind you one thing. I have spent a lot of the membership fees from all of you to buy a lot of market reports. So please, please, please download them. You can find all the market reports here in optica.org/market reports. It's very simple. You go there, optica.org/market reports, and you select the market reports that you need. At the bottom of the page, you put your email address and they come to your inbox. No need to remember any password or anything like this. Select what you want, put your email, they come to your inbox. It can't be any easier. Thank you very much for making a dream come true. So the Optica network, for building this global industry platform. Thierry, Andrew, all the attendees, have a fantastic day and see you soon. Bye-bye.
Thank you, Jose. Bye-bye.
Thanks, everyone. Bye.